60 Brinell, a head-hardened rail grade has 350 Brinell. So we are in the crossing area, we are even higher than a head-hardened rail under operation. This just some slides to explain how these crossings could look like or how the design is done. So the crossing compact 1400, which is actually an easy design. The crossing point itself, the crossing nose, is made of a tempered steel. This gives you an strength of 1400 Newton per square millimeter, which corresponds actually with the hardness of a head-hardened rail. And at the end of this machined block, we are going to weld standard rail section, which are machined to fit to the crossing nose. The wing rails, they are also made out of standard rail sections. They are machined band, and the whole crossing is assembled by use of blocks and high tensile bolts, mainly M27, to form a very rigid unit. This design is also used worldwide in many railways. Is a proven design and actually a very simple and easy design, because this can be adjusted to any alignment what is required, and for production there is no pattern necessary. So cost-wise this is quite an economic solution. The more complicated is the cast manganese crossing. The green part shows the manganese part, which is cast, and at the four ends we are going to flash part weld standard rails to these four ends. And for this welding we actually developed, I think already more than 30 or 35 years ago, a special welding technique, because directly manganese cast steel and rail steel you are not able to weld together. So we are using a kind of an intermediate rail section and austenitic material, where we are welding this section on the rail, then we are cutting it back, then we are welding it on the manganese part, and actually between the manganese part and the rail steel there is just a 10 mm part of the austenitic material left. And this actually allows us to produce cast manganese crossings, which can be fully ceramic welded into track. In the past, I mean, the technology of cast manganese crossings is already very old, but the main problem was that ceramic welding was not possible with manganese steel. So these crossings were actually fish plated into the turnout, and when the technique of the long welded track comes up, this actually did not correspond with this technique, and they were looking for a solution to that the cast manganese crossing also can be welded into the track. The disadvantage, let's say the disadvantage for dual gauge turnouts, the disadvantage is that you need a pattern for these crossings, which are rather costly. If you produce these cast parts for a turnout where you have 100, 200 or 300 pieces, the pattern actually doesn't make a big amount at the end of the project. But if you have to cast just one or two pieces, then actually the pattern costs will rise up the total costs of the turnout significantly. Patterns are in a range of, depending on the size, 20 to 30,000 euros. One. If you have different types, as we saw on the second slide, there are 28 types. If you're using a few of them, and for each type you need a cast pattern, then you're ending up very soon with €500,000 of pattern costs. But unfortunately there are some configurations where cast manganese crossings are the only solution for dual gauge turnouts. This picture just gives an example how it can work with the type compact 1400. So it is a, I would say, not a special design. There are just two crossings behind each other. It's a kind of a standard design. There can be also thermal weld into the turnout, and actually this is not really a big deal from point of design and from point of production. The more complicated actually we saw on that slide. This is actually the only picture I have of this example. So this is already quite a complex design to have all these flares, crossing points, guiding areas incorporated in one cast block. And actually our standard is that all rail contact surfaces are mechanical machined on a CNC machine. So this block is going on a CNC machine, and all flangeways, crossing nose, all areas which are in contact with the wheel, they are mechanical machined on a CNC machine. Good. In connection with crossing, there is also one of the main components, which is the check rail. There are also two solutions available. The standard solution, which is also an advantage for in regard of maintenance, is that we are using the check rail profile 33C1, which is placed on a chair or bolted on a chair without having any connection to the running rail. So this actually allows us, if this check rail is wearing, we're just going to loosen the bolts, putting shims between the chair and the check rail, tighten the bolts, and actually the check rail is set to the proper check gauge and provides a safe run through to the crossing. When the check rail is worn too much and not readjusted, then there is it could be happen that the wheel is hitting the crossing point, the crossing nose, damaging the crossing nose, or in the worst case, it is going into the wrong crossing flangeway and causes a derailment. So this is quite a simple design, also used in all modern railways around the world. The alternative solution is to use a different profile which need to be bolted to the stock, or to the outside rail. That actually gives you a fixed flangeway which cannot be adjusted in operation. So if this check rail is worn off, there are two possibilities. Either you're going to replace the check rail, or you're going to do a kind of build-up welding and grinding in the guiding area of the check rail. The reason why I'm introducing this solution here, this is rather, I would say, an old solution which is not used anymore with many railways. The big advantage of this solution is that it is a narrow design. If you compare the width of this arrangement with the width of this arrangement, so this needs much more space. And as we have heard, in dual gauge turnouts, there are certain areas where we have very less space. So this could be actually seen as a section out of a drawing, where we are using outside for this, at this rail, for this crossing, to guide this crossing, we are able to use the 33C1 check rail, which is placed on separate chairs. You see these chairs here, they are fixed with two bolts on the sleepers. It's quite a wide design, but there is still some space in this area, so we are going to use this here. But for the narrow gauge, we also need to protect the crossing nose, this one, the gap, with a check rail. So as in this area there is very little space the only chance was to going for this narrow profile, which is to be bolted directly to this rail. Having a look on a photo, there it could be seen very easy. This is the 33 C1 jack rail with the, I would say, long chairs, and this is the directly to the rail bolted jack rail profile 48 C1, which also provides a super elevation of the jack rail, same as the 33 C1 jack rail. So in this area, it's the only chance to have a proper guidance for this crossing to use this jack rail profile. Of course, the disadvantages I have mentioned before, it is not that easy to maintain if it is worn. Then there are some further design aspects that at the beginning of a project, actually you have to consider the wheel sets, the wheels itself, the axles, the back-to-back dimensions of the vehicles, of the locus, of the wagon, which are going over these crossings. So this needs to be done actually as a first step before you start designing these turnouts, and check, are we able to provide a safe solution for crossings and jack rails which accommodates all different types of wheels, axles and vehicles. And actually, if this is not possible, then the only chance is to go to movable point crossings. So fixed crossings, as shown there, is not possible anymore. Then movable point crossings have to be used for the single crossings, also for the obtuse crossings, if they are in the design. Because the big advantage of the movable point crossings is that they are closing the gap in the running edge, and you don't need a jack rail anymore. So movable point crossings movable point crossings can accommodate all different combinations of wheels, as there is no interruption in the running edge. So they are passing through the turnout, the wheels can pass through the turnout as on a standard track. Further, there are, I mentioned it right in the beginning, there are some turnout configurations which requires obtuse crossings, same crossing type as used in diamond crossings, where you're just crossing two tracks under a certain angle. These types, they are mentioned in the table before. All these types, they are using, or they requires obtuse crossings. So obtuse crossings, they are limited from the angle so that they are still safe. And actually, if you only have one obtuse crossing, I think I will move to the next picture. This would be the area where the obtuse crossing would be, but as you do not have another obtuse crossing opposite as on diamond crossings, you are not able to maintain or to guide through the gap which would occur in a rigid crossing. So the solution would be to get actually rid of the obtuse crossing and to build in a movable obtuse crossings actually, which is closing this gap and which provides a continuous run through of the wheels. So here it actually could be seen that this curve actually is intersecting or interrupted by this straight rail, and actually this ends up in a very, very small angle, which would create a very long gap or unguided length in the obtuse crossing, which is not, which actually could not be maintained because there is nothing on the opposite side. Basically, the use of movable obtuse crossings is a, I would say, quite good solution for the wheel overrun, for the, I also would say, for maintenance. The disadvantage is that for a movable obtuse crossing, you need 2 sets of switch machines locking, so the full set of ALT equipment, which also need to be actually then incorporated in the interlocking station at the end. So this actually, the impact of dual gauge turnout actually moves also in changes, in possible changes in the interlocking system. So the dual gauge aspect cannot be concentrated on the track part only, so that it is also influencing signaling side. Additional switch machines are required and additional slots or places in the interlocking station. Further, which actually might simplify some crossing configurations, we are able to provide a special switch design where we can change the third rail from one side of the track to the other side of the track. I think I will move on to the next slide. That makes it more clear as the text on the first slide. So I think this one is the easier to understand. We have a broad gauge line, we have a standard gauge line here where the third rail is close, in this case, to the right hand rail, and we can provide special switches which has a kind of an S-shape design where we move with this rail to the right hand rail, and actually we would end up with a new third rail on the opposite side. And this could be a quite important device to simplify some types. For example, a turnout type 10, which would have an obtuse crossing, which might be or need to be designed possibly with a movable obtuse crossing, could be converted to a type 12, which just has 2 single crossings. I think I will just go back to the table. That makes it possibly more clear. So we have type 10. We have the third rail on the left hand side. The letter P means we need to use an obtuse crossing, but by moving or changing the third rail to this side, we are ending up with such a configuration where we just have 2 single crossings just behind each other. So by using such a special switch device, I can have some influence which types of dual gauge turnouts can be used in the network. And just having a quick look on such a crossing configuration on one of the pictures. This would be such a configuration, which is much more simpler, cheaper, easier to maintain as a movable obtuse crossing we had just before. As this one, which need to use additional ALT equipment. So there are two configurations available. As let's say the basis track in this case would be the broad gauge track. We are moving the narrow gauge track, or the other way around is actually that we leave the standard or the narrow gauge track, we leave that constant and we are just moving the broad gauge track, the rail from one side to the other side. This is also something what we already have built. This is a current or a photograph what was taken recently in our Spanish factory. They made some device also for a project for ADIF. I think it must go somewhere on the Spanish-Portuguese border where these two lines have to intersect or will be connected. These switches are made with a radius of 1500 meters, and due to the long radius they are requiring at least 4 setting levels. The possibly disadvantage of such a system is that you need somewhere quite a lot of space to install it, I don't know, right in front of the turnout, or maybe it's possible to install it somewhere outside of the railway station or wherever. The overall length of this device is in this configuration is with 38 meters. I'm quite sure that the length could be reduced if you're going for a smaller radius, but then actually the speed on this, yeah, I actually do not have an English name or word for that. In Spanish they call it, I think, compitador de hilo. We also have a German word, but there is not an English expression. Is actually, I asked, but it is, nobody knows an English word for that. Yeah, but I think if you're going to reduce the radius, length can be shorter, but actually then speed on these two switches need also be reduced.
Speed only on the track that changes?
Only on the, if you're changing the side of the gauge. If you're going in the straight, line speed can be go over. Line speed is the same, yeah. It's just, if it's the same condition as if you're going in a turnout through a switch device into the deviation.
So you can choose which gauge you sacrifice the speed?
Yes, exactly. Okay. Just a few words to maintenance issues. I mean, you already saw that due to the special design, there are some design compromises on crossings, on switches, on jack rails, on plate works, on actually on everything. So compromises requires higher attention under service. Design compromises needs higher attention under service. So in regard of maintenance, what will be the impact in dual gauge turnouts? Due to possibly shortened wing rail flares in space restricted areas, there are higher impact forces. Thus, there will be higher wear on the wing rails. Possibly, there are reduced parallel flangeways in guiding areas. The result is you're ending up with shorter overrunning areas in the crossings. Therefore, you have higher impact forces on crossing points. Higher impact forces also end up with more wear, more load on a very small area or surface. In case of use of the jack rail profile, the narrow one, for the 8C1 in space restricted areas, you are not able to adjust the jack gauge by just inserting shims. You have, as explained, either to replace it or to do a kind of build-up welding and grinding to adjust to the proper jack gauge. And if you have to move to movable point crossings, independent if these are single crossings or obtuse crossings, additional maintenance of movable parts like greasing are necessary, and also additional ALT equipment need to be maintained. So switch machines need to be checked, rodding need to be checked, clamp blocks have to be maintained, greased and reset. All these things come in addition. So coming to the end, as a conclusion, we would say basically all types of dual gauge turnouts could be designed and manufactured. All critical issues as mentioned in the introduction could be solved and handled in the design by means of the proposed design solution. So the last slides about switches, crossings, check rates, I think we are quite confident also to find or to design solutions for the Iberian and standard gauge turnouts if there will be the chance. But I mean, this is, I would say, not really satisfied as a final conclusion. Therefore, but for an economic final solution of the track work, it should be taken care already at stage of alignment planning to avoid the most complicated types of dual gauge turnouts and to avoid types with obtuse crossings. Technical solutions are there, they just need to be used by the planning companies, consultants or whoever is doing it. And further, by having less complex turnouts of having less complex types of dual gauge turnouts in the network, turnout investment costs, costs for additional ALT equipment, costs for additional setup in the interlocking station, installation costs and maintenance costs can be reduced or even avoided. So that would mean at stage of planning there should really be taken care, and types of turnouts need to be simplified. And actually such projects need to be viewed from system perspective. So the departments for planning, department who is responsible for track and turnout, for signaling and maintenance, only these together they can achieve an optimum economic solution for all parties. There is no help if the planning department is coming up with an alignment plan and has no idea what can be used, what technical solutions are there. So I think that might be one of the keys of success, to introduce a proper working and a system with less maintenance, a system with, I would say, less costs for dual gauge turnouts. Yeah, this was the last slide. Thanks for your attention.
Thank you very much.
I hope it was not too technical in some points, but I rather thought going really into detail and point out the critical issues, make it visible on existing projects, how the things look like, and yeah.
Okay, then stop.